in a sense, the first method we saw here was actually solving systems by graphing, but for one, graphing isn't always the very easiest thing to do, and for two, graphs aren't always the clearest in terms of being able to locate points of intersection. So for things like our first couple of examples, those happen to be at nice round numbers, but even then the scale might not be perfect for guesstimating precisely what we're looking for, and those were still nice numbers. The solutions to systems of linear equations don't need to be nice things. If we want to, we can deal with situations where our coefficients are all irrational numbers, which means we are very likely to get solutions that are all irrational numbers. And when that happens, it's very hard to tell the difference between root 2 and root 3, for example, in terms of their space between the numbers 1 and 2. It's not really obvious, even if you have a lot of practice with these sort of things, at telling where that's supposed to be, so we need methods for being a little bit more precise. And the first one we have here is using the substitution method, where substitution essentially says, let's take our pair of variables and replace one with another to simplify it down, and then just do some basic algebra with the remainder. So for this, our process that we're going to be working from says that we're going to first solve either of the equations for one variable in terms of the other, that is, get x in terms of y or y in terms of x, then substitute the expression found in the first step into the other equation, then solve the equation containing one variable, back substitute the value found in step 3 into one of the originals, where you can simplify from there to find the remaining value, and then to be sure you probably want to check. So with each of the methods we're going to see here, we're going to get the setup, the sort of process that we want to work from, and then we'll see an example for how it's going to work. So for our first example, we want to solve the system 3x plus 2y equals 4 and 2x plus y equals 1 using substitution. So for this, what we need to do here is recognize our system and then try and isolate one of our variables, where in that second equation, we have 2x plus y equals 1. So we can very easily pull over the 2x and get, instead, y equals 1 minus 2x. And what that allows us to do is look into our first equation, that 3x plus 2y is equal to 4. And everywhere we have a y, we'll plug this in instead. So we'll have 3x plus 2 times 1 minus 2x equals 4. And then we'll simplify this a little bit. 3x plus 2 minus 4x equals 4. Subtract over a 2, add in a negative 4 and a 3, and what we're going to end up with is x is equal to negative 2. Again, pull that over, that becomes a 2. Pull these together, that's a negative x, divide out the negative, and we get x equals 2. Where from there, technically, we want our fourth step that we had, and I sort of flipped through these quickly because once you get the process, actually writing out the steps is a bit more than you usually need to do. But for that next step in there, what the book might expect you to do is to plug this back into one of the originals, but the truth is you don't need to plug it into one of the originals. Usually the adjusted form is going to actually be a lot easier. So we can take this value there and plug it into that one instead. So I'm going to take x equals 2, and we'll have y is equal to 1 minus 2 times 2, or y is equal to, that should be negative, which means this is not a negative 3, because that's a double negative there, and this would end up becoming 5. Lost my confidence there because I lost that negative. It happens. In any case, we have that our solution set, even though it's a single point here, would be the set of ordered pair, negative 2, 5. And you can check this by plugging it back into our original system there. I'll leave that to you at this point. We've done a lot of these things before with this checking of the values, checking that these things work. I'm not going to go through that process because it's just plug and chug again. This is the sort of thing we did in that first example. We've done it a lot. But this approach is kind of predicated on having that nice place to start. Substitution is usually the more popular method because it has, in my opinion, a little bit less ambiguity. there that like you understand you're trying to solve and replace, and it makes sense to solve and replace and push back, whereas addition, it's a little bit hazier, it's a little bit more abstract. I didn't like it as much in high school algebra, and I expect a lot of people will have similar apprehensions about it to me, but we're going to see that it's actually a bit more widely and easily applicable for cases where this doesn't immediately present itself.